The statement of Gauss Divergence Theorem is like this. If say capital V is the volume bounded by a given surface say S, and vector F is a continuously differentiable vector. Then, so this is triple integral over the volume V of the divergence of vector F into differential volume, that is dV, should be equal to double integral over the surface, the vector F dot ds, or the right hand side can also be written in some of the books. You may find that this is S into vector F dot n cap into ds. Okay, one of them you can write. So, but the left hand side is still going to remain same. Alright, so this is the statement of the theorem, but we solve various problems based on this. So question number 1 is, say if vector F is equal to 2x squared minus 3 times z into I cap minus this is 2 times xy into j cap minus 4x into k cap, right? If this is the case of vector F, then evaluate triple integral over the volume V. This is del dot vector F dV, where V is the region bounded by the planes. What are the planes? First one, x equal to 0, y equal to 0, comma z equal to 0, and 2x plus 2y plus z equals to 4. Alright, so this is the required area or the region which we have to use to solve this problem. Okay, now first let us perform the del dot f. Del dot f should be equal to, right, the del operator is dou by dou x into I cap plus dou by dou y into j cap plus dou by dou z into k cap dot the given vector. So that is 2x squared minus 3z into I cap minus 2 times xy times j cap minus 4x into k cap. So under this condition, now we can write this is equal to, I have to perform the dou by dou x of 2x squared minus 3z plus dou by dou y of minus 2xy plus dou by dou z of minus 4x. So this is equal to, the first term is dou by dou x of 2x squared is 4x, then dou by dou y of minus 2xy is minus 2x, and the last term gives a 0 value. So this is del dot f, divergence of f is equal to 4x minus 2x equals to 2x. In the next step, so we will find out the range of z from the given data. So right, from the given data we can see that x is 0, y is 0, z is 0, correct? So z actually starts from that point. So therefore, right, z varies from, this is 0, 0 to, there is an equation which is 2x plus 2y plus z. From that I can write z is equal to, this is 4, which is already present, minus 2x minus 2y. So z varies from 0 to this point, right? Whenever z is equal to 0, I can try to write a different notation for y. Okay, so when z is equal to 0, this implies, right? From the above equation, put z equal to 0 in the above equation. This implies I have 2x plus 2y equal to 4. This implies x plus y is equal to 2. So this implies, what is the range of y? So y varies from, y is 0 is one of the points. So 0 to, this is 2 minus x. Because take x to the other side, you get y is equal to 2 minus x. Right, now we have the condition z is also 0 and y is also 0. So next condition, when z is equal to 0 and y is equal to 0. So when z is equal to 0 and, let us write y is equal to 0. When both are 0, right, let's use the same equation, right? Y is 0 and z is 0. So if you use z is equal to 4 minus 2x minus 2y, right, we get the 2x equals to 4. So this means x is equal to 2. In the sense, x varies from, you can see that it's already mentioned, x is 0 is one of the point, extreme point. So it starts from 0 and goes till 2. So therefore, now we are supposed to perform the triple integration. This implies triple integral over V, the vector f, uh, this is del dot f dot V. So this is equal to, we'll be writing in this fashion. So this is del dot f dv should be equal to, so let's put the limit of x varying from 0 to 2, y varies from 0 to, this is 2 minus x, and z varies from 0 to 4 minus 2x minus 2y. All these values we identified, all the ranges have been identified from the given problem. Okay, so this is equal to, z is equal to 0 to 4 minus 2x minus 2y, right? The function del dot f has already been calculated, right? And we have the value with us. Okay, so let's just go back and check that value. So you can see that del dot f is equal to 2x. So that 2x I'm going to write here. This is 2x. dv is a differential volume. The smallest possible volume is x coordinate, y coordinate into z coordinate, dx, dy, dz. Right. So, but we'll write them in such a way that we follow the order of integration. So, innermost integral is z. So, I write dz. Then the integral is with respect to y. So, dy. Lastly, we are going to perform the integration with respect to x. So that's why we have these terms present. So this is equal to, now keep the first two integrals as they are. So that is equal to integral x is equal to 0 to 2, and the next integration is y becoming equal to 0 to 2 minus x. Perform the integration, right? So there is a 2, I'll write the 2 outside. So x remains inside as it is. The integration of this function gives you a z, and it should vary from 0 to 4 minus 2x minus 2y, right, into this is dy dz. So this has to be equal to 2 times integral x is equal to 0 to 2, and integral y is equal to 0 to 2 minus x, right, x into, so when z is equal to 4 minus 2x minus 2y, we have this term minus 0 into the dy dx, sorry, this has to be dx. All right, this is dy into dx. All right, let's perform this integration now. So this is equal to 2 times integral x is equal to 0 to 2, and integral y varying from 0 to 2 minus x. So this is 4x minus 2x square minus 2xy times dy dx. So in the next step, we have to substitute this is equal to x is 0 to 2. Let's do the integration with respect to y. First term becomes 4xy. Second term minus 2x square y. Okay, and the last term should be, so we have the 2y into x is 2xy. So this has to be minus 2 times, I think we have a 2 written outside, correct? So I have made this is 2 times. So minus this is 2 times x y square divided by 2, this will cancel, into dx. So we should substitute the values from 0 to 2 minus x for every y. Each and every y will get this substitution. So this is 2 times integral x is equal to 0 to 2, right? This is 4x, this is 2 minus x, right? And when it is 0, this term is 0, so minus 2 times x square into y is a 2 minus x, minus x times, this is 2 minus x the whole square into dx. Okay, so let us expand this now. So this has to be equal to 2 times integral x is equal to 0 to 2. Let us expand the term. So this is 4x into 2 is 8x. 4x is into x is minus 4x square. This is minus 2x square into 2 is 4x square. This is minus of minus is plus 2x cube minus, so x into, this is 2 square is 4 plus x square minus 4x dx. Alright, and in the next step, this has to be equal to 2. X is equal to 0 to 2, right? We have 8x minus 8x square plus 2x cube minus 4x minus x cube plus 4x square into dx. Okay, so this results in 2 times 0 to 2. Let's write the terms containing x this has to be alright. So this is, we can write it as minus of x cube, then x square terms are only minus 8x square plus 4. This is minus 4x square. Then we have 8 minus 4x is, sorry, this is 2x cube minus x cube is a plus x cube. So please correct. This is a positive quantity, so this is plus x cube minus 4x square. Then we have plus 4x into dx. So now we need to integrate this function as it is. So this is 2 times x cube becomes x to the 4 by 4 minus 4 times this is x cube by 3 plus 4 times x square divided by 2. This cancels with this as 2. Substitution should take place from 0 to 2. 2 times 2 comes over there as this becomes 4 minus 4 into 8, 32 divided by 3 plus 2 into 4 is 8. So upon simplification, we are going to get the answer as 8 by 3, which is the required answer. Okay, let's go to the next question now. So this is to verify the Gauss the Gauss Divergence Theorem for the vector function, right? The function is denoted by f vector is equal to, this is x square minus yz into I cap plus this is y square minus zx into j cap plus z square minus xy times k cap taken over the rectangular parallelepiped given by 0 less than or equal to x less than or equal to a, 0 less than or equal to y less than or equal to b, and 0 less than or equal to z less than or equal to c. Okay, so this is the given question. Now we'll try to solve this by applying for verification of the divergence theorem, or the simply it's called as divergence theorem, or we can call it as the Gauss divergence theorem as well. Okay, so to start with, let's write the required function or the statement of divergence theorem as follows. So this is, I have to prove that triple integral over a given volume V into divergence of vector f dv should be equal to the double integral over a surface S, the vector f dot ds. So f is given, already given, right? Let's write the f. So what is the f? This is x square minus yz into I cap plus this is y square minus zx into j cap, then we have plus z square minus xy into k cap. So we can see that this is the given vector f. So if you want to perform the del dot f vector, then we are going to differentiate the first component, that is the component along x-axis of this y vector with respect to x. So we get a dx over there, dou by dou x of, this implies the dou by dou x of x squared minus yz plus the dou by dou y of y square minus zx plus dou by dou z of z square minus xy. So this means this is equal to dou by dou x of x square is 2x. Dou by dou x of yz is 0. So going to the next term, this gives me 2y and 2z, right? I can rewrite this as 2 into x plus y plus z. Alright, so now when we have this particular function shown as here, it is very clear that, right, our next intention is nothing but we have to take the triple integral. So we'll start with the left hand side of the Gauss divergence equation, that is triple integral over V the divergence of f vector into dv. So we know the complete limits of x, y as well as z for this given function. So this is equal to triple integral, but we'll put the values of x, y, z now. So it is x is given as 0 to a, y is given from 0 to b, and z is given 0 to c. Have to perform this into divergence of the required function is 2 times x plus y plus z into x plus y plus z into dz into dy into dx. Okay, so this is equal to, let's take the 2 outside, integral x is equal to 0 to a, integral y is equal to 0 to b. Perform the integration of this function with respect to z, right? So I get this is x z plus yz plus this is z square divided by 2 with the substitution as 0 to c. This is dy dx. Okay, in the next step I'm going to simplify this and substitute the values of c. So that should be like this. Put the value of z as c. Okay, so this is equal to 2 times integral x equals to 0 to a, right, integral y is equal to 0 to b, right, put the z value as c. So this is xc plus yc plus c square by 2 into dy dx. Now I need to perform the integration with respect to y. So this is now equal to 2 times integral x is equal to 0 to a. Perform the integration. So this is xc into y plus this is y square by 2 into c square by 2 into y varying from 0 to b dx. This is equal to 2 times x is 0 to a. Substitute the value of y. So first term becomes x c into b plus this is b square c by 2 plus this is bc square by 2 whole multiplied by dx. Therefore, in my next step, I am going to perform 2 times. This is x square cb by 2 plus b square cx by 2 plus bc square x by 2 from 0 to a. So this is, I can see that the 2 cancels with all of them. So this is a square bc plus ab square c plus ab c square. Okay, so this is what is the answer that we are going to get now. Next part, so we just have written the required answer only for the LHS. Okay, now we have to write the right hand side. Right hand side is nothing but, so let's write this. So this is the LHS. Okay, so we'll write the LHS as follows. So I am supposed to perform the double integration over a given surface area. This is vector f dot n cap ds. Okay, so now using this, let's try to write a diagram corresponding to what we are exactly doing. So let's say the x, y, and x, y, and z coordinates we are going to write now. Like this. So now what we are drawing here is the required parallelepiped. So this has to be from this point to this point. Alright, so the next line should connect these 2 points. Okay, then another line we have, this should connect these 2 lines. Then we have the fourth line connecting the last 2 points. Okay, so this is the parallelepiped which we were looking at. Now let's give some names for them. Okay, so the names are, say this is the origin O. I'll call this point is A. Then let me call this point is B, and say this point is C. Then we have the other points like E. Let me call this as F, and this is the point P. So C is here, E is here, A, origin. Let me call this point as B. Okay, this is P, this is F, this is B. So now the unit vectors, let's mark. If I call this axis as x-axis, then this becomes the y-axis and the vertical axis becomes z-axis. So let's mark the unit vectors. So this is a cap, this is j cap, and that is a k cap. So now we need to identify how many surfaces we have, because see, the equation says that you are going to perform an integration, right? Double integral over a surface. So which surface to take for this given diagram, right? It is equal to the total number of surfaces that it has. So if you check, right, the number of faces that you are going to see here is equal to 8. So what we do now, so let us define each and every surface, right? For on every surface I should do this integration. Then only I am able to get the proper right hand proper RHS calculation. So let's do this. So we will look at the parallelepiped which we have written, and we'll write the faces of this one by one. Okay, so the 6 faces are, we have how many faces? 6 faces. So this is okay, the 6 faces are, let's give the notations now. S1 is O A D B, that's the bottommost surface. Then we'll write S2 O C E. Then S3 can be written like this is O B F C, backside surface. Then S4 is nothing but this is C E P F. S5 is BFPD, and S6 is ADPE. So it means, right, we have 6 different surfaces. For each of these surfaces, we need to have a unit vector, because the equation says that double integration over S, the f dot n cap ds. So n cap is the standard notation for perpendicular term. Okay, so S1, X2 are the 6 phases with the respective outward unit normal okay unit normal vectors. So for the first one it is minus k cap, next one is minus j cap, minus I cap, comma k cap, comma j cap, comma I cap. So we understood 6 different surfaces, right? The 6 different surfaces, and then we found this. Okay, so first one, let's do the integration one by one, right? So first surface, that is for surface S1, I am supposed to perform double integral over surface. This is the vector f dot ds. So this means I have to perform a double integral, right? But the double integral is for the given surface S1, right? X varies from 0 to A, and y varies from 0 to B. Okay, so this into, we have xy dy dx. So why this is xy dy dx? Because z is equal to 0. So in the f, right, in the vector f, put z equal to 0, and since n cap is equal to only minus k, only the k terms, right, only the term containing k will be retained. Okay, so this is equal to integral x is equal to 0 till a minus 0 to this value. So this first term becomes x into y squared by 2 from 0 to b into dx. So this is equal to, so instead of writing an integration, let me simplify this here. So this has to be equal to, so when I put b over there, this is b square divided by 2 minus 0 into, so put x equal to b, so that gives you, so that becomes x squared by 2. So x squared by 2 should be substitute 0 to 2. So this part S1 is a square b square divided by 4. Similarly, let's go to the second one, that is the second integral, that is, say for S2. I'm performing the same similar integral. So this is double integral over S. Previous one we'll call S1. Now let's call this as S2. The vector f dot ds is equal to integral x is equal to 0 to a and integral z is equal to 0 to c, right? This is z into x into this is dz into dx. So this is x is equal to 0 to a. You have x into this is z square by 2 from 0 to c. This is dx. Correct? So this is c square by 2 into the x becomes x square by 2 and values are 0 to this is 0 to a. So therefore this is equal to, we have c square a square by 4. Now we'll go ahead and calculate the other values, that is S3. So this is for the third region, the double integral over S3, this is vector f dot n cap ds is equal to, this is y varying from 0 to b and integral z varying from 0 to c. This is yz dz dy. So if we solve carefully, we are going to get b squared c squared divided by 4. Very similar to the previous step. Then we'll go for the next S4. We are supposed to calculate double integral over S4. This is f dot n cap into ds. This has to be equal to, this is integral x is equal to 0 to a integral y is equal to 0 to b. See, my function becomes equal to, this is c square minus xy into dy dx. So now this is equal to integral, keep the first integral as it is, that is 0 to a, and apply the integration to the function with respect to y, that is c square y minus this is xy square divided by 2 from 0 to b dx. Okay. Now this is equal to integral 0 to a, this is c square b minus b square by 2 into x dx. So as a result, now we are going to do the integration with respect to x. So this is equal to So the first term is c square b into x from 0 to a minus, there is a b square by 2 outside, x becomes x square by 2 from 0 to a. So this function is going to result, this is a b c square minus a square b square by 4. Alright, this is for the S4. Then let's move on to fifth one. So this is for S5, right? I am supposed to calculate integral over S5, the vector f dot n cap ds. So this is equal to integral. Now x is equal to 0 to a, and the second integral will be z equals to 0 to c. So we have the function b squared minus zx into d, perform dz, then dx. Similar to the previous problem, if we solve, we are going to get acb square minus a square c square by 4. Alright, and the last area needs to be integrated now. So that is going to generate something like this. So that is for S6, this is double integral over S6, this is vector f cap dot n cap ds. Okay, so this has to be equal to, now in the final integral, the integration happens with respect to y is 0 to b and integration z is equal to 0 to c. Then you write the f dot n cap ds. So that is a square minus yz into dz dy. So after solving this double integral, we are going to get a square bc minus b square c square divided by 4. So which means now I need to calculate the overall value, that is from each and every integral that we have performed so far, we are going to get this answer. That is, therefore the RHS is equal to double integral over S, this is vector f dot ds, should be equal to, see the first term we got a b c square, second term we got a c b square, and the last term is a square bc. So this will be equal to the LHS. So since we can see that the LHS is equal to RHS, we can say that hence proof. Like this we can prove a problem based on the Gauss divergence theorem.